Thank you. Yeah, so thank you for that lovely introduction and also for welcoming me onto the agenda today. It's been a lovely event. I've really enjoyed it so far. Just a little bit of background about me. So I did an undergraduate degree in physics with medical physics. Then I did the NHS scientist training program in what's now clinical scientific computing. Finished that in 2019. Did a little bit of a sidestep into clinical informatics, so working more with data analysis, big data sets, routine administrative healthcare data. My current role is as a clinical scientist in an external assessment group for NICE, based here in Newcastle. And more recently, I have turned my hand to some economic modelling, which I'm going to talk about today. So for context, we were commissioned to undertake an early value assessment of robot-assisted surgery using 6 different devices for orthopaedic procedures, so total and partial knee arthroplasty and total hip arthroplasty. The process takes us 6 weeks. In that time, we've got to find and review clinical and economic evidence. We have to build an early economic model. We have to seek and incorporate opinions of clinical experts. Then we have to summarise all of the evidence, all of the results of the modelling into a report. So there's a lot to get through. And the key aim here was to rapidly, very rapidly, develop an early economic model which compared robot-assisted surgery with conventional surgery to inform further evidence generation. So the clinical area that we're talking about is arthroplasty. So it's typically used in cases of osteoarthritis. It is used in trauma as well, but the primary use is in arthritis. And it's a surgical procedure basically to cut away the damaged or worn out joint and replace it with a prosthetic joint. The little image here shows that in our knees we have 3 compartments. So we've got a tibio-femoral compartment, which is where the tibia meets the femur, and we've got 2 of those, one on the inside of the knee, one on the outside of the knee, and the patellofemoral compartment is where the femur meets the kneecap. So when we're talking about knee replacements, it can be a total knee replacement where all 3 of the compartments are replaced, or a partial knee replacement where only 1 or 2 are replaced. And robot assistance is intended to enhance the work of the surgeon by giving better precision, flexibility, and control. So this is an image of one of the robots, and basically what the arm does at the end of the robot, that can be used for anything that the surgeon would normally do, so cutting the bone, helping with aligning the new joint, and it removes some of the physical burden from the surgeon. So we used the R-Decision package. It is available on CRAN. The main reason we used it was familiarity. It was developed by our head of department, Andrew Sims, and we had used it for previous projects, although not to the extent that we did for this one. Other reasons for using it were transparency. It's very easy to see how the variables are being used, more so, and we've heard this a couple of times over the last couple of days, more so than Excel, where you can't necessarily see what the cells have in them and what links to what. In terms of speed, it was very fast, both in terms of development time, because there's plenty of vignettes. We had sort of code snippets that we could reuse from previous projects. And in terms of quality assurance, again, because of the transparency, it's very easy for somebody who hasn't coded the model to look at the code and check that all of the values going in there are correct. There's a lot of automation as well, so we don't need to recode the Markov engine from scratch as we would if we were using Excel. There's checks built in to make sure that our probabilities add up to 1, that the cohort only make allowed transitions, and it's really easy to trace and fix any errors, and also easy to rerun if we need to. So I'm going to be focusing on a total knee arthroplasty example, and this is the workflow that we used. So first thing that we did was define the model structure based on published models. I'm not brave enough to do any live demos here, so I've just got a few little code snippets. Next thing we did was create the health states. Basically, they all go into a list, 1 state per line. We created the allowed transitions, again, a list, 1 per line. And then we build the model, which takes in the states, the transitions, cycle length, and the discount rate that we want to use. So this was the model we used. So we've got 6 states there. We assume that the path that people take is the same for manual or robotic surgery. So they'll have their surgery, they'll move into the well after primary surgery state. And some of them will go on to have a revision surgery, either because they've got an infection or maybe the joints sort of come loose. After that, they move into a post-revision state where we account for a 12-month utility decrement after the revision surgery, and then they move into a well after the first revision surgery state. And of course, from any of those states, they can move into the death state. So back to the workflow then. Next step was to create the transition rate matrix. And actually, I should have pointed out on the previous slide, although the diagram I shared there wasn't the one that is spat out by R-Decision, it does also generate the model diagram if you need it. I just developed this one before I got to that point in the code. So we now create the transition rate matrix just using the matrix function from base R with 1 row and column per health state. We use the probabilities that we know that we've found from the literature, or indeed dummy variables if we haven't got that far with the evidence review. And we set up the transition rates from state to state. We add the self transitions to make sure that all of the rows sum to 1 at the end. And then we set our input parameters. So we've made it this far without needing any input parameters in terms of costs and qualies. So now we put those in, again, 1 per line. So the parameters we used, we assumed a lifetime time horizon based on a life expectancy of 100 years. We had a cycle length of 1 month, which would allow most of the patients who'd had surgery to be moved out of the surgery state into the well after surgery state. We discounted at 3.5% for both costs and utilities, and we assumed the same revision rate and mortality rate for conventional and robot-assisted surgery, and they were based on annual reports from the National Joint Registry, and we extrapolated based on standardized mortality tables. So in terms of cost parameters, the companies provided the costs themselves. It included the robotic system itself, consumables, the implant, servicing, training, annual procedure volume to account for small hospitals, bigger hospitals, expected lifetime of the system, and whether CT imaging is needed before surgery, because it's not needed for all of the robotic technologies that are available. Other costs were the HRG costs for replacement and revision. We assumed they were the same between both arms, and all we were adding on to the robot-assisted arm was the costs of the robot itself. We looked at the length of stay, and again assumed that this was the same for both conventional and robot-assisted surgery in the base case. Utility parameters, we only had values available for baseline and 1 year. We had utility parameters for post-revision. We applied a decrement for 12 months after revision surgery, which was different depending on whether that was due to infection or other reasons. We also, as a bit of a sensitivity analysis, looked at the upper and lower confidence intervals for utilities, and we assumed that utilities were the same for all of the robotic technologies because all of the evidence was actually on one robotic technology. Things that we varied for sensitivity analysis were purchasing options, because some companies offer capital purchase instead of rental, some of them offer volume-based purchasing, so we wanted to encompass as many of those options as we could. We varied the annual procedure volume to account for smaller, bigger hospitals. We changed the HRG cost for the primary procedure, just in case it was cheaper. We looked at implant cost, and we varied that across a range given by one of the companies. We reduced the length of stay for the robot-assisted arm, and we changed the proportion of patients who had a revision surgery after robot-assisted surgery relative to conventional surgery, just to account for the possibility that the robot-assisted surgery is more accurate in terms of the alignment of the joint and therefore leads to fewer revisions. So then once we'd set the inputs, we ran the model, and this just loops over every year in the time horizon, and then we get a report at the end. What we found was that robot-assisted surgery was dominated by conventional surgery. Point estimates lay close to the y-axis on the cost-effectiveness plane, suggesting there was some uncertainty there. We found as well that the results changed direction across the 95% confidence interval that we used for the utility values. So at the lower confidence interval, robot-assisted surgery was still dominated by conventional surgery, but at the upper limit, it was actually cost-effective. And the only way that we could, in the sensitivity analysis, make robot-assisted surgery win was when there were 0 revisions at all in the robot-assisted arm. So limitations of the work, we found that the model was sensitive to changes in primary procedure costs, which contributed most of the overall lifetime costs. The utilities, as I've said, were only available for a single technology, and they were from a small RCT, and there was no statistically significant differences in the utilities between the 2 arms, so this was identified as an evidence gap. There might also be differences in mortality and revision between conventional and robot-assisted surgery, or between specific robots. The National Joint Registry does now collect this data by robot, but it's not yet over a long enough term for us to be able to use it reliably for this. The model doesn't account for any short-term events, adverse events arising from the primary surgery, so things like bleeding and infection that didn't lead to a revision, so we assumed that they were accounted for in the initial HRG cost. It also doesn't account for benefits of robot-assisted surgery for the operating staff. It's quite physically demanding, so there could actually be some benefit there that isn't the patient benefit. Doesn't account for any additional set of time in theatre, and the data didn't allow for probabilistic sensitivity analysis, although we did push it as far as we could with the univariate analysis that we did. The strengths, the main strength was the rapid development of the model. We managed to cover 6 technologies, 3 procedures, so we had 18 base cases, plus another 18 and 18 looking at the different utility values, and then all of the sensitivity analysis on top of that. There was no way that this could have been done in Excel in that 6-week period. It was easy to rerun the model as new information came to light. Because we are reviewing clinical and economic evidence in parallel, and because we were checking costs with the companies and we were receiving new costs, changed costs, and there were occasions when the model needed to be updated and rerun. We did manage to, so tables could be outputted automatically using R Markdown, so less chance of transcribing errors, copy and paste errors, and we were able to highlight the key uncertainties and clear evidence gaps that could be filled by future research. So all of that was enough to satisfy the NICE committee, but it did bother me that many people are used to seeing models in Excel and are used to being able to sort of play with it themselves and see exactly what's going on. So I thought that we should probably try as a proof of concept and see if and how easy it would be for us to provide something that does the same as a model in Excel from the user perspective, but with the benefits of the R model we developed underneath it, just to give better accessibility and user friendliness for non-R users. And then, of course, it's easier, as we're keen to do, to justify moving away from Excel. So again, I'm not brave enough to do a live demo of this one. I can't claim all of the credit for this, so I started it. I sort of wired in the inputs, the outputs, made sure the model was running okay in the background, and then I handed it over to our STP trainee in clinical informatics. She took it, she developed it further, she made it applicable to all 3 of the procedures, and made it look much better than I did. So what we've got here on the left-hand side, you can choose what procedure you want to use. You can look at the demographics, so that will give you the option of starting age for the cohort, and what percentage of males and females you want in the cohort. Down the left-hand side below that, you've got costs, and I will say that all of these costs and utilities that you can see on the screen are dummy values. I just set them randomly to take a screenshot. So you can set all of those down there, and then you've got an output on the right-hand side which just summarizes all of the inputs that are currently active. We've got an output at the top in the middle that is the costs, the utilities, and the ISA. And then we've got a Markov trace at the bottom there, so we can see how many people are in each state each year for the two arms. So in conclusion, we were able to rapidly produce an early economic model using R-Decision. We identified the key uncertainties and made recommendations for future evidence generation. And ultimately, which was the goal of this, was to support the NICE committee in their decision making and development of the guidance. I just want to finish with a quick shout out to the National Joint Registry. Although we weren't able to use the data that they provided because we didn't have enough events in terms of revisions and mortalities split by robot, they were really responsive, really helpful, yeah, it was really well appreciated that they were willing to send us any data at all. So thank you very much, and I'll take any questions.
Thanks very much, Rachel. Now, just as you're coming to the end, my internet connection is getting flaky. Dawn has got two lovely questions, so in a moment I might invite her to come along and give the questions. But just while I'm good on the microphone, I just want to ask my own. So I think you've got that kind of the bio that I think we'd all love to have in terms of that the training where you're coming from, having a physics background in terms of making yourself very sort of quantsy and so on. I'm sure moving into health economics has been much aided by these established tools that are out there, and you gave a very clear rationale for why you chose this particular tool that you were using here. And you outlined some of the benefits of the problems that you can avoid. Can you think of any stumbling blocks that you came up on when you first were using this tool? Because this wasn't your first application of it. You've used this package previously as well. Is that right?
So I had used it previously for a previous project, but somebody else actually built the model. So I made all the changes, and I put the parameters in, ran the model. But this was the first time I was actually building it from scratch.
Yeah, and that's quite a different experience when you're doing it yourself. So, yeah, I mean, one of the things I was thinking about in particular, I don't know, I presume the model does allow for different cycle lengths at different points in time in the model, because I know you use a monthly time horizon, a monthly cycle throughout the whole model, but I presume there must have been some discussion. Would a shorter time cycle be useful for catching sort of short-term sequelae around the joint recovery and then moving to a longer cycle? Was that something that came up as a discussion, or?
Not really. I think the main challenge was the sort of time that we had available to do it. It's very hard to be able to sort of incorporate all of the things that you'd want to in the 6 weeks. The other thing is it's an early model, so if there was any talk, it would have been that it's probably a little bit too complicated for that sort of early stage modeling. But that's definitely worth considering for the future, and it could be done in terms of different cycle length at different points if that was helpful.
Yeah, and this isn't an observation on R, but just more in general. Like, I remember looking around for evidence on the cost effectiveness of these interventions in general, and for such widely practiced interventions that we spend so much money on provide such quality of life benefit. There's a real dearth of evidence on these, at least when I've gone looking for them. So it's nice to see more evidence being generated. Dawn, do you want to put your two questions to Rachel?
Yeah, cool. No, really nice demonstration, Rachel. Thank you very much. And I can see why a system like this is perfectly suited to NICE's early value assessment. I assume that's what we're seeing here, yeah? So I'm just thinking in the more general sense. So I've looked at quite a few kind of one-size-fits-all Markov modeling packages before, not this one. But every time I've always found it's not flexible enough for a full HTA model. It may well be flexible enough for something early like this. So what I was wondering was, did you find any limitations where you're thinking, oh, the package doesn't do this, if only, for your example? And why this particular package over any of the others? Have you got like any pros and cons?
Sorry, what was the first question there?
Did you ever find yourself thinking, oh, damn, the package doesn't quite do what I wanted to do?
No, again, I think with it being an early economic model,
Yeah.
I think we just kind of accepted that, the limitations are as they are, and, we'll present what we can around that.
Yeah.
The advantage was anything that I did feel it needed or was perhaps missing, and with it being developed in-house, it was very easy for me to sort of take 5 steps from my office to the office next door and say, Andrew, we need this in our decision. Can you can you help, please? In terms of using different packages, I think the main reason for this one is the sort of familiarity and the support within the department. It was slightly less of a learning curve for me under time constraints, knowing that we had used it before and there were examples there that I could draw upon.
Yeah. That makes a lot of sense. And then I'm really interested to know exactly how NICE used the app within the decision making. So was it at the committee meeting? Because I would absolutely love to see that happen.
No, sorry, I should have made it clearer. We actually did the app, and it's actually still in development. There's a few more pieces that Evelyn, our trainee, is busy working on. We didn't actually get that done in time for NICE to see it, so NICE haven't actually seen that yet. It's something that we probably will share with them just to get their feedback on whether it would be useful in future assessments. But yes, I agree, it would have been probably very useful for the committee to have seen that in person. And yeah, that's something that we'd love to do in the future.
Yeah, there's probably even a spin-off paper there. If you were actually able to ask the committee what use they made of it, and did they find it useful, you could. I wonder if they were to facilitate you and give them their feedback on the tool, it could be something useful, because what happens behind the closed doors is always a problem to know. Do the decision makers really use these? Do they find them useful, and do they have the expertise to interpret things appropriately? We never get a chance to really look at that. So I don't know. I guess